Friends, welcome to the 35th lecture titled Rings and Chain Links, which is an extended study of curved beams what we discussed in the last set of lectures. This is under module 2 advanced structural analysis of the course offshore structures under special loads including fire resistant design. We do agree that offshore structures of compliant type are generally moved to the seabed. In fact, compliant type and floating type are generally moved to the seabed using mooring lines, chain links, cables, wires, etc. So, it is interesting for us to understand what would be the nature of stresses which are acting on these chain links and rings, so that we can design them in a proper manner. Let us take a typical chain link to understand the failure mode of this. Let us say there can be an issue related to the failure in the welds. Let us say this is a typical weld. The intradas part can have a fatigue damage, the crown part can also have a potential damage when the chain link is subjected to axial pull or push. Essentially, it will be pull. There are different failure types which can be envisaged in these kind of chain links. If I say different failure modes, there can be possibly a fatigue crack, at inner or inter grip area. So, there can be failure due to fatigue crack occurring at the intergrip area. The second can be within this length there can be a distortion. So, there can be distortion in the chain dimension which can take place along its length. Thirdly, there can be a fatigue damage at the weld. Fourthly, at the intradas part and the extradose part here erosion can take place. Can occur at the intergrip area, and in this sector there can be gouging. Gouging can occur on the external surface, which can lead to propagation of cracks. So, there are different failure types by which a chain link can fail, and the chain link fails. Obviously, we understand that the station keeping of the floating vessels cannot be ascertained. For our study now, let us consider a closed ring and work out stresses in a closed ring. A typical closed ring is drawn in the figure. Let us say it is subjected to forces of axial pull P. Let us take an horizontal axis of symmetry AB and of course mark the centroidal axis of the cross section and mark these dimensions as RI, RO, and this becomes R of the centroid, which usually called as capital R. Once the ring is subjected to the force P, then let us try to draw the split part of the ring let us mark the forces to which they are subjected. Let us say this is my force P, which will be acting on the system. Now, this will be resisted and opposed by P by 2. In addition, there will be H acting and they are again in equilibrium. In addition, there will be also a moment which will be acting as shown, which are again in equilibrium at the marked section. Please note the moment MO has a tendency to increase the radius of curvature. It means at any point here, mark this as let us say A1, at A1 it will cause tensile stresses, and at the corresponding B1 it may cause compressive stresses. Having said this, let us consider a thin circular ring with a circular cross section. This is subjected to pull P. Let us try to draw the free body diagram acting on the section AB. Let us say is subjected to MO. There is a force, as we just now saw, P by 2 acting here. To maintain the equilibrium, P by 2 is acting here. Let us take a strip whose length is ds, whose length is ds at a radius r, at an angle strip theta, and the included angle is d theta. We know that this distance will be r cos theta, and we also do agree that this distance is of course r. The figure shows free body diagram of the ring segment under the pull P at section AB. AB refers to this one at section AB. According to Castigliano's theorem, the equation with respect to this is 0, where U is the strain energy. The bending moment MB at the considered section will be now equal to M0 minus P by 2 R minus R cos theta. Actually, I am looking for this distance, and this is going to be clockwise in nature, caused by P by 2, and M0 is anti-clockwise in nature. Therefore, the resultant moment MB will be given by equation 2. One can always say this further simplified as minus PR by 2 1 minus cos theta. Now, let us say partially differentiate this with respect to the moment and make it to 0. That is the application of Castiglione's theorem. So, now this is for the length L, mb by EI, dou mb dou m naught, the differential length of the strip ds, and set it to 0. Let us say dou mb by dou m naught is actually dou by dou m naught of mb is given by m naught minus Pr by 2 1 minus cos theta, which is very easy to understand, is going to be unity. And also the elemental length ds can be also expressed as r d theta. You can see here the elemental length ds can be expressed as r d theta. Hence, dou u by dou m naught is integral 0 to L m b by E I dou m b dou m naught ds, and that should be set to 0. There are 4 segments. So, let us say 4 varying from 0 to pi by 2, that is the validity of theta. M b is actually m naught minus P r by 2 1 minus cos theta, let us say divided by E I, because I want E I here, and dou m b by dou naught is unity and ds is r d theta. Set this to 0. Simplifying is going to be 4 r by E I 0 to pi by 2 m 0 minus P r by 2 1 minus cos theta d theta, and this should be set to 0. Further, integration of 0 to pi by 2 m naught minus P r by 2 1 minus cos theta d theta will be equal to m naught theta minus P r by 2 theta plus P r by 2 sin theta, limits 0 to pi by 2, which will give me m 0 pi by 2 minus P r by 2 pi by 2 plus P r by 2, which gives me m 0 is P r by pi pi by 2 minus 1. I call this equation number 4. It is very important to see the sign convention here. The sign convention in the above statement is m 0 is considered to be positive, which means that m 0 increases the radius of curvature of the ring by causing tensile stresses inside and compression outside. So, that is very important. Now, we would like to know bending moment at any angle theta, which is given by m b is equal to P r by pi pi by 2 minus 1 minus P r by 2 1 minus cos theta r is equal to P r by 2 cos theta minus 2 by pi. Now, it is interesting to note that m b will be 0 for cos theta is equal to 2 by pi, which means that theta is about 50.43 degrees. Now, at the loading point, we know that theta is pi by 2. Here bending moment should be the maximum. So, I should say m b maximum is P r by 2 cos pi by 2 minus 2 by pi, which will be equal to minus P r by pi, equation number 7. Now, if you really want to find the stress at any angle theta, then let us mark this figure. So, we understand here it is going to be p by 2 for equilibrium, and we also know this is the sign convention what we are using for m 0. Let us consider at any angle theta there will be stresses as shown here. One will be the normal stress to the surface, one will be the tangential stress to the surface, and these two will set in a resultant. As we know very well now this angle, so this angle is theta, it will be now subjected to m b, and m b is actually equal to P r by 2 cos theta minus 2 by pi. The vertical force results in two stresses, which is normal stress and the shear stress. Where the normal stress is given by P by 2a cos theta, because this is going to be P by 2a, and the shear will be P by 2a sin theta. We also know that combining the stresses at intrados and extrados, we now say stress is simply given by m b by a e of y plus e by y plus r plus P by 2a cos theta. This is positive because it induces tensile stresses. So, in this equation we know tensile stresses are positive, that is very important. And friends, you should recollect that this equation what we have written here is actually equation derived for curved beams. So, we will do a numerical to understand how this can be applied directly for a given problem. Let us say we will have a numerical example. Find the stresses induced in a circular ring for the data given below. It has got a circular cross section. The diameter is 20, subjected to a load P, which is 5 kilonewton, and inner dia of the ring is 100 m. So, let us draw a ring. It has a circular cross section. The ring is subjected to a vertical load or a pull, which is 5 kilonewton. Let us take a cross section and try to find the stresses at this point. We know that this is R I and d I is 100 millimeter. Therefore, R I is 50 millimeter. R outer is going to be 50 plus 20 millimeter, because that is the diameter of the cross section. Therefore, the diameter of the ring small d is 20 millimeter, and therefore, the radius is 10 millimeter. This is for the cross section. This is for the ring subjected to a load which is 5 kilonewton, so many newtons. We all know that the CG of the circular section is at the center. Therefore, R will be now 50 plus 10, which is 60 millimeter. So, I can mark R which is 60 millimeter. We already know from the equation to calculate E, E is the eccentricity of the neutral axis from the centroidal axis. Which we have explained very clearly in the lectures on curved beams, and E is given by R minus R square twice of R minus root of R square minus R square. Please refer this equation for the curved beam discussion with a circular cross section. Let us substitute in this case, which is 60 minus R square, okay, twice 60 minus square root of 60 square minus 10 square, which gives me E as positive 0.4196 millimeters. So, we also know bending moment at any angle theta is given by MB is equal to PR by pi pi by 2 minus 1 minus PR by 2 1 minus cos theta. So, let us say at section BB we understand that theta is 0. Hence, MB is what we say MB at BB is PR by pi by 2 minus 1, because the second term goes away. Let us substitute P 5000 Newton, R 60 pi by 2 minus 1, which gives me the moment as 54507.04 Newton millimeter. Since the cross section is subjected to a direct force, there will be also a direct stress which will be tensile, which will be given by P by 2a cos theta. So, now we are looking for section BB where theta is 0. Hence, the direct stress at section BB will be simply P by 2a. Area in our case is pi r square, which is pi 10 square, that is the area of my cross section, which is 314.15 mm square. Therefore, the direct stress at section BB will be 5 10 power 3 by 2 314.15, which gives me plus 7.96 Newton per mm square, plus indicate it is tensile. So, that is the first part of it. I also want to find the bending stress. To find the bending stress, we need to do a small exercise. Let us say this is my circle. Let us say this is my O plane, and we know that this is my centroidal axis, this is my neutral axis, and we do agree that there is a shift of this, which is E, which we know, which we computed, and we know that this distance is R I and this distance is R O. I want to know the distance of the innermost fiber and extremmost fiber. So, I call this as y I inner and this as y outer. So, obviously, y inner will be, we know that this value is R. So, R minus E minus R I. Let us substitute all of them, 60 minus 0.4196 minus 50. So, this is plus 9.5804 millimeter. Similarly, y outer will be in similar terms. I want to find this distance is going to be, one can say, simply the diameter plus E, which is 10.4196. This is negative because this is heading towards the compressive stress. Therefore, y I is plus 9.5804 and YO is minus 10.4196 millimeters. Once I have the distance of extreme fiber from the neutral axis, I can now compute the bending stress using this equation, which we already derived in the curved beams section. So, stress at intradas is stress direct plus stress bending. Stress direct is tensile 7.96 plus stress bending at MBB is MB by AE YI by RI, which will be plus 7.96 plus 54,507.04 divided by 314.15 and E is 0.4196, and this ratio is YI distance of inner fiber 0.4 divided by RI is 50. So, I get this value as plus 87.2 Newton per mm square, plus indicate it is tensile. As expected that the moment is increased in the radius of curvature, inner portion is in tensile, which we are also getting verified from the results. Similarly, stress at the outer DOS is again sigma direct plus let us say sigma bending. Sigma direct is again tensile all the time, whereas this will be minus 54507.04 divided by 314.15 into 0.4196. This is going to be Y outer by R outer. Now, Y outer is negative in our case, therefore, plus 7.96 minus 54507.04 by 314.15 into 0.4196 multiplied by 10.4196 by 70. So, the minus sign of Y0 is actually taken care of here, which gives me minus 53.59 Newton per mm square, and that is going to be compressive. I will give a small exercise. Go back to this figure. We have found out the stresses at the section BB. You can always find a similar section which is at some angle, let us say AA at 45 degree. So, the exercise is determine the stress at intradas and outradas at section AA, which is at 45 degrees from the centroidal axis XX. So, you know the equations for MB, you know the equations for N. One can obtain the normal stress and find sigma normal, and one can find the bending stress, bending moment, and then find bending stress both at intradas and extradas bending, then combine them to find the stresses, as you can check at 45 degrees. I think you can be able to straight away apply the equation derived and substitute them properly to get the answers. So, friends, in this lecture we discussed the method to estimate bending stress in a circular ring. Rings and chain links are common in mooring lines. So, in mooring line analysis under special loads, you need to understand how to estimate stresses using the curved beam derivations what we discussed in the last lectures. One example problem explains you how to estimate the stresses in the intradas and extradas of any section drawn across the circular ring to estimate the stresses at this point, both direct and bending stresses at interdars and exterdars. We have also explained how to use the proper sign conventions for M0 and the stresses as you apply in the equations. Thank you very much.